paper 2-1, May June 2023 of Cambridge ASA Level Physics Examination Board. My name is Nariman Mealim, and here you can see my email and mobile. This is the cover page, paper 2 level structured questions. So there will be questions with many sections. Here we see data and some formulas that will be provided. Question 1. Define power. So for power we have two definitions. Power is work done per time taken, or power is energy transferred per time taken. Why? Because work done equals energy transferred. How much energy is transferred from one form into another, so much work is done. Use the definition of power to show that SI-based units of power are so much. So we write formula power equal work time, then we split work into force time distance, then force we split into mass time acceleration, and now we know all base units. Mass is in kilogram, acceleration meter per second squared, distance meter times second. So we substitute these quantities by their base unit and we get the result. So this question is done. Intensity I of sound wave moving through the gas is given by this formula, where F is frequency of the wave, A is amplitude of the wave, V is the speed of wave, and K is constant that depends on the gas. Determine SI base unit of K. So we rewrite formula for K. We have intensity divided by this expression. So intensity is power by area. So base unit will be, we use previous result for kilogram meter squared second minus 3. We divide by area minus meter squared. We get kilogram centimeter minus 3. On the other side, we find that frequency is second minus 1, area is meter squared. Here we have mistake. Meter squared. And meter squared, and velocity is meters per second squared. So when we divide 1 by this expression, we get second cube meter minus 3. So we should multiply intensity by this 1 over. So when we multiply, we simplify, we get kilogram meter cube. Actually it is density. Depends on the gas, of course. Here we have complicated picture, so I'm going to split my screen. Okay. And now let's see which question accompanies this picture. Just a moment, let me find. Okay, a rigid uniform beam of weight W is connected to a fixed support by a hinge as shown in figure 2.1. So this figure, A compressed spring exerts a total force 2.8 to 8.2 Newton vertically upwards on the horizontal beam. A block of weight 100 Newton, 0.30 Newton, rests on the beam. The right-hand end of the beam is connected to the ground by a string at an angle of 30 degrees to horizontal. The tension at the string is 4.8 Newton. The distance along the beam are shown in figure 2. So here we have pivot is hinge, so beam can rotate about this pivot, and we have some forces producing clockwise moment. It is weight of the beam, block weight, and part of the tension, component of the tension that is vertical. Also, component anti-clockwise moment is produced only by spring, and all information is force is given and distance are given. Shows that the vertical component of tension in the spring 2.4 equals 2.4, sorry. Yes, so vertical component is opposite to angle 30 degrees, so sine 30 give us half, so 2.4. This question is done. By taking moments about hinge determines the weight of the beam. So moments about hinge are equal and opposite. Moment clockwise 2.4, 2.4. 2.4 is vertical component of the string of the tension plus all these distances plus moment produced by 0.30 Newton, moment produced by weight W. This is moment clockwise, and moment anti-clockwise is only due to spring. The value is 2.8 Newton and distance is 0.5. After doing simple arithmetic, we get the value of 1.6, giving answer to three significant figures as 4.8 is given to two significant figures. Calculate the horizontal component of the force exerted on the beam by the hinge. So horizontal forces are equal, hence the horizontal component of the string, 4.2 Newton, equals to force produced by hinge. The spring obeys Hooke's law and has elastic potential energy of 0.32 joule. Calculate the compression of the spring. So here we have two solutions. One is pure algebraic solution. So force equals K times extension, energy equals 1/2 over K extension squared. Dividing this one expression by another, we get delta x. Or you can use standard method. It is force over extension is straight line for Hooke's law, and energy is area under the graph. So under the graph we have triangle, so 1/2 force, which is height, by base, which is delta x. The string is cut so that the spring exerts extends upwards. This causes the beam to rotate and launch the block into air. The block reaches the maximum height and then falls back to the ground. Figure 2.2 shows the part of the path of the block in the air shortly after it hits the ground. So it was at point A and touches the ground at point B. Calculate the decrease in gravitational potential energy of the block for this movement. So change of potential energy equal mg delta H. Mg is given, it is weight, and delta H is shown on the picture. So we calculate value 27,000 joules, thousandths of joule. Use your answer in C and conservation of energy to determine the speed of block at point A. Total energy at point A, higher point, equals total energy at ground. So total energy at point A consists of kinetic energy and potential energy. Total energy at the ground is given. So kinetic energy is half mv squared, Potential energy at point A we calculated before. After doing some simple arithmetic, we find that it is 1.1 meter per second. Here on the side I show how to find mass. Mass equal weight over g. G is always 9.81. By reference to the force on the block, explain why the horizontal component of the velocity of block remains constant as it moves from A to B. In this direction, zero resultant force, zero acceleration, constant. As a result, the horizontal component of the velocity constant. The block passes point A at time t and arrives at point B at time b. On figure 2.3, sketch a graph to show the variation of the magnitude of the vertical component Vy of the velocity with time from Ta to Tb. Numerical values are not required. So ball is moving as projectile and horizontal component doesn't change, but vertical component increases and gradient of the graph equals acceleration. It is constant and it is equal to g. So we assume that at point A there is some initial velocity which increases. Question 3 need another picture, so let's put the picture above. Just a moment. Here is the picture. Let's read the question. A block is pulled in a straight line along a rough horizontal surface by varying force x as shown in figure. So we have momentum, we have force, rough horizontal surface. E resistance is negligible. Assume that the frictional force exerted on the block by a surface is constant and has magnitude 2 Newton. The variation with time of momentum of the block is shown. State second Newton law of motion. Resultant force equals change in moment by time taken, or in symbols F equals delta P over delta T. This is one of the versions of the second Newton's law. In IGC it is resultant force equals mass times acceleration. At A level you should consider resultant force as change in momentum by time taken. Use figure 3.2 to determine the block for the block of the time the magnitude of resultant force on the block. So figure 3.2 is this figure, and change in momentum by time taken is gradient of this graph. So we find gradient and we get 1.5 Newton. So change in momentum by time taken. The force, resultant force, because this is resultant force, it equals 1.5, but we have also friction, so the force F equals 3.5 Newton. On figure 3.3, sketch the graph to show the variation of force X with time from 0 to 6 seconds. So we, at the previous graph, we can see, just a moment, where is the previous graph, that till 4 seconds we have force. We know the value of force 3.5, and then there is no change in momentum, so resultant force is 0. And it is 0 because our force F is balanced by friction. So graph consists of two steps. One is 3.5 as we found in previous subsection, and another is 2 Newton to balance to make object to move at constant velocity and constant momentum. Beaker. Okay, let's find beaker for the top screen. Here is the beaker. A beaker in air contains a liquid. The base of the beaker is in contact with the liquid and has area A, as shown in figure. The liquid has density ρ and fills the beaker to a depth h. By using definition of pressure and density shows that P equals ρgh, where ρ is the pressure due to the liquid as exerted on the base. Where P is the pressure due to liquid that is exerted on the base of the beaker, and G is acceleration of free fall. So, first of all, pressure is force over area. Force is actually weight of the water, mg, and area is area at the bottom of container. Then mass equals density by volume, rho v. V equals area by height. So simplify, cancelling area, we get rho gh. So this question is done. We should suggest why equation in A does not give the total pressure of the base of the beaker. We should take into account atmospheric pressure. So total pressure will be atmospheric pressure plus pressure from liquid. Figure 4.2 shows the variation of the total pressure inside the liquid with depth x below the surface. And what we should find? Determine the density of the liquid. Okay, so pressure is rho gx, gradient of the, if we draw graph of pressure against x, gradient will be rho g. Gradient equals rho g, rho equal gradient by g, gradient equal delta p over delta x, using graph at the points that we can read accurately, it is beginning and the end. Gradient is 750, 7,500, I think. No, mistake is here, right? So density we found from this graph, we found density 765 kilogram per meter cube, a bit less than water. Water is 1,000. A solid cylinder is held stationary by a wire so that the base of the cylinder is level with the surface of the liquid. So we see that because object is in equilibrium, the weight of the object is 0.53 Newton, and this is why it is held by wire. The cylinder has length, cross-section area, tension in the wire is so much. The cylinder is now lowered and then held stationary by the wire so that the top of the cylinder is level with the surface of the liquid. Calculate the new tension in the wire. So new force appears, it is upthrust, and upthrust equals the weight of liquid displaced by the block. So mass of the liquid multiplied by volume of the block. Weight we know, tension plus upthrust equals weight of the block. Tension will be weight minus upthrust, and we get 0.42. An electromagnetic wave, question 5. Electromagnetic wave in a vacuum has wavelength so much. States the name of the principal region of electromagnetic spectrum of the wave. This you should memorize. So at A level, some values, typical values for wavelengths, for masses, for temperatures, you should memorize. Calculate the frequency is in terahertz. Also, this you should know. Tera is 10 to the 12. Also, some information should be memorized. So, we use wave equation. Speed of wave equal for frequency by wavelength. We rewrite this for frequency. Wavelength is given. So we get to two significant figures, we get 36 terahertz. An arrangement that uses a double slit to demonstrate the interference of light from a laser is shown. So we have double slit and screen at distance 2.8 meters. The light from laser has wavelength so much and is incident normally to the slits. The separation of the slits is A. The slits and screen are parallel and separated by distance 2.8. An interference pattern of bright fringes and dark fringes is formed on the screen. The distance on the screen across 8 bright fringes is 22 as illustrated. The light waves emerging from two slits are coherent. State what is meant by coherent. Same nature, same frequency, constant phase difference between the waves. Calculate the separation. So, separation of the slits. It's not slits, it is fringes. 22 millimeters over 8. So we get distance between fringes. Fringe P is central bright fringe in interference pattern. Fringe Q and fringe R are the nearest dark fringe and nearest bright fringe respectively to the right of the fringe as shown in figure 5.2. Calculate the difference in the distances, the path difference from each slit to the center of Q. So, because here we have dark fringe, path difference will be half of wavelength. So we divide wavelength by 2 and we get answer. State the phase difference between the light waves meeting at the center of fringe R. Fringe R is bright, so phase difference is either 0 or 360 to have constructive interference. A metal wire in a circuit has a length, I think we don't need pictures anymore. A metal wire in a circuit has a length of so much, cross-section so much, total number of free electrons in the wire so much. There is current in the wire so that the charge of so much coulombs moves past a fixed point in the wire in time of 2.5 seconds. Show the number density of the free electrons in the is so much. Okay. Here I see some mistake. Okay. So number density is number of electrons by volume of wire. So number of electrons by volume of wire. Wire is cylinder. And when you are calculating, don't forget to use brackets. Brackets for calculator, because calculator doesn't know that you divide by all of them. You should use brackets. If you do it, you'll get answer, and you should round it to two significant figures, because number of free electrons is given, as you see, 8.5 to two significant figures. Calculate the average drift velocity of the free electrons. This is favorite formula. Current equals nave. N is density of electrons, A is area, V is drift velocity, E is charge of carriers or electrons. Rewriting formulas for V and finding current is charge over time. We using arithmetic, we get answer. Not very big drift velocity, small, 10 minus 5. A battery of electromotive force EMF 9.6 volt and negligible internal resistance is connected to the series to two fixed resistors and thermistor as shown. Here I think we need to split screen. Calculate the current in the resistor of resistance 5800. So we know voltage. We take closed loop, for example this loop, and here we have EMF 9.6 volt and voltage is 6 volt. So the rest is potential difference across resistor 5800. To find current, we divide potential difference by resistance and we get this value. Another closed loop, 9.6, calculate the resistance of the thermistor. Another closed loop, 9.6 plus IR total. So we take now this big loop and total resistance is sum of all resistance including resistance of thermistor. So we know total resistance, we know two resistors, and we can calculate thermistor resistance. So this is the result. C. The initial energy of the stored in the battery is so much. Assume that EMF of the battery is constant. Determine the final energy stored in battery after charging of 330 has moved through it. So voltage or EMF equals energy over charge. Rewriting this formula for energy, we have voltage multiplied by charge. So we multiply, we get answer. Because they ask left energy, so this is initial value, 2.6. We subtract with the same order value spent, and if we do it, we should not forget, of course, should not forget 10 to the fourth. So this is my mistake. 10 to the fourth. Joule. Quite enough energy. So environmental conditions change, causing the increase in thermistor of the resistance of the thermistor state, whether it's decrease, increase, or change. Temperature. So, because resistance of thermistor increase, temperature decrease. Current in the thermistor decrease because total resistance increase. Potential difference across resistance increases. Why? Because it now share it now take more share of potential difference. Last question. An isolated stationary nucleus X decay by emitting alpha particles to form a nucleus Y. Nucleus Y and nucleus Z are isotopes of the same element. By comparing the number of protons in each nucleus state and explain whether the change of nucleus Y is less than, greater than, or the same as the charge of nucleus Z. Isotopes Y and Z have the same number of protons and charge. Charge of nucleus, of course, of nucleus. They ask about charge of nucleus. Yeah. Nucleus X, 2 protons left and charge of Y is less than charge of Z. Use the principle of conservation of momentum to explain why nucleus Y cannot be stationary immediately after the decay of nucleus A. First, nucleus is stationary. Alpha particles leave the nucleus at very high speed. To conserve momentum, so momentum at the beginning is 0, then suddenly we have alpha decay. So alpha particle is moving at high speed. It means that nucleus, although it is heavy, should also move in opposite direction. So should have velocity in opposite direction. And this is the end of our past paper. Thank you for your attention.